Hi everybody, welcome back to another exciting video. In Black Body Engineering, this is the channel where you and me will be building a 32-bit CPU. Today's video is all gonna be about the instruction memory, the source where we as a user are gonna use to store our program. By the end of this video, you'll know exactly how instructions are fetched, how is the instruction memory structured, what Indianness really means, and how to wire everything together in Logisim. So what exactly is an instruction memory? Well, an instruction memory is a place like it's like your cookbook when you're gonna cook. It has a bunch of recipes and you go one by one page at a time as you progress in your recipe. So let's talk about how is this memory instruction memory structure in our CPU. So this is the instruction memory. For the sake of this video, we're gonna implement this as a ROM, so read-only memory. We're gonna write all the programs here, so we can write the first instruction here. And this is where we're gonna store everything. This is gonna be address 0, 0, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1. And we're gonna have a counter that is gonna point to the first address of this instruction memory. This address is always gonna add with a 4. So the next instruction is not gonna be 1, but it's gonna be 4. So it's gonna be 0, 4, 8, and 12. And that's how the counter is gonna count. For the sake of this um, program, let's write a really quick MIPS program. So let's say we want to add this number. We want to add the register 1. We register 2. So this means that ST1 is going to get added to. So we're going to add this register with this register, and the result is going to get stored in our register 0. So the following instruction in machine code is going to be hexadecimal 0, 1, 1, 2, alpha 4, 0, 20. So each of this um, box is going to store 8 bits, so 1 byte, and 1 byte is 8 bits, and in hexadecimal is 2 characters. So that's 1 byte, 2 byte, 3 byte. Oh, I made a mistake right here. Okay, and that's a 4 byte. So this is byte 1, byte 2, byte 3, byte 4. We're gonna store this in our instruction memory in a scheme called Big Endian. I'll explain in a second what is that. Just follow me. So 0, 1, 2 alpha, 40, and 20. And this is gonna be our instruction stored in our instruction memory. And the CPU has to grab all 4. This is our instruction memory. and it has to grab those 4 boxes, all those 4 bytes, and it's gonna output that 32-bit word with the full word. So it's gonna output 01 to alpha 4020, and that's gonna get, and this is called fetching, and that's gonna send to the rest of CPU, to whatever is using it. It might be the LEU, it can be the data memory, to whatever it needs it inside that CPU. So now that we explained that data path, it's clear that we have to understand what is Big Endian. So our memory is byte addressable, means that we don't store 32 bits as a whole chunk. We store in little chunks. We store in 8 by 8s. So the first one is 8 bits. The next one is 8 bits. Next one is 8 bits. The program counter, it holds the address for the next instructions, and that helps us store our words in 8 bits instead of 32. So originally there's two ways of storing information. There's Big Endian and there's Little Endian. And the way it differs is, let's say for example, the instruction that we have 01 to alpha 40 and 20. You saw that we stored that in the following order. Yeah, and that is because we're using the Big Endian. So this is my instruction memory, and the output is gonna be 01 to alpha 40 20. It means the most significant bit is stored in the least significant address. Now, if we talk about Little Endian, it's the opposite. We will have to store the other way, 20, 40 to alpha 01 in order to output 01 to alpha 40 20. We're gonna be using Big Endian on the CPU, so the output matches our comprehension. Technically, if I guess, like some CPUs like Intel, I don't know about AMD, they will use Little Endian, but for us, it's okay. We can use Big Endian for the purpose of this video. Now you will be wondering, how are we gonna put all this together? So for the purpose of this one, I'm gonna demonstrate you how to implement the instruction memory. It's gonna be a ROM, the address bit width. So Logisim has a limitation. The maximum bits that I can input into the system is 24 for 16 megabytes. My data bit width, I'm gonna leave it at 8. I'm gonna make it quad because I need multiple address. Okay, this has to be 24 bits to access the 4 memories, and then I have to get the, where's the splitter, west, I'm gonna put it center, 4, 4. This is my output. My output's gonna be 32 bits. And then I'm gonna program the ROM. I'm gonna say AB, AB, okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, AB, C, D, E, F, close that. As you can see, my first address. So right now it's on Little Endian. So one way that we can fix this is to change the order. This. So now it's defined as Big Endian. And if I want to go to the next instruction, remember that our program counter is going to add address plus 4 every single time. So we need address 4 here. So now I'm in the second address, A9, A, B, C, D, and E. And this will be a very simple instruction memory. However, this is not what I want. So I went ahead and implement possibly a closer to the real one that I want. As right now, I only have 128, I think it is. 16 times 8, so 128 megabytes. Technically, I need 4 gigabytes. However, Logisim does not have that capability, and I will have to implement many ROMs and and try to link them together, and that will probably cause my program to crash, and I don't want that. So I had to use some ingenuity here to implement this. So these bits that are here are going to control my multiplexers, and that's going to route the proper output of the ROM to my instruction memory output. Right now I'm in address 0, so I'm in this one, in this ROM. So I have A, B, C, D, E, F 56, A, B, C, D, E, F 56. So this will be my actual instruction memory. I can put a program here, continue here, and my program is going to be able to address all those values all the way until this bit gets activated. Bit 27 will zeroize my counter and it will go back to 0. So if I try to enable this, I try to speed it up, you can see how my counter is going one by one. Eventually you're gonna see this one click, and then eventually you're gonna see this one go high, and then I added full adder here to add that +4 value that I need to keep it always adding by 4. You're not gonna see this one, at least not quickly, to go to this value, but right now I'm in this ROM, and that's what I'm outputting. It's all 0 because I mean it's all empty, so I don't have any information loaded right now. So this is my instruction memory. Eventually we're gonna load a program in here and we're gonna see the CPU execute. So I hope you enjoy. For this video I show you how our instruction memory is holding our program. I told you that each instruction is 4 bytes. I told you that the program counter adds by 4. And how are we using ROMs to store our data. Hope you enjoy it, and if you want to keep learning, like, subscribe, and comment if you hit any problem. I'll try to answer everything that I can. And thanks for watching another video on Black Body Engineering.